what we're going to talk about in this short video is the Guerrilla RF p-hemp process and the IP3 behavior versus biasing, which we learned about early on, like we did a lot of the stuff. We found that with the 207X series, the 208X series, the GRF 4002, 4003, 4, and 5, any of our p-hemp amplifiers, 5110. What we found was, when I ran the data on them, one of the first things I would do when I got a new part, or we were developing a new part, is I would set my voltage, and I would sweep my V enable, therefore sweeping my IDDQ and measuring IP3. And what we typically see on a one-stage device, this applies to single-stage devices, which are the bulk of them. The IP3 curve versus IDDQ would behave as such. So there'd be a peak IP3. So when I developed the data sheet, it was a no-brainer to set my bias current where IP3 peaked. Over time, perhaps over many products, that was generally the case, but perhaps not in every case. The other day, I was looking at what part number. Let me check and see what part number it was. It was a 2070, and I saw that the standard bill of materials for our standard evaluation board was set for a bias current of 90 milliamps, which is a little high. I'm thinking, why is that? Is it process variation? Turns out it wasn't. It was just at some point, a board got built with a higher bias current, and the BOM folder got populated with that BOM. So when I looked at it, I was looking at the IP3 and I was saying, that's a little lower than I think it should be. I swept the current. I looked at the IP3. I saw a peak at 70 milliamps, not 95. I looked at the data sheet, reference current 70 milliamps. Okay, we had a little bit of an error, so I redid the standard BOM with a different bias resistor, which would set the bias current where it belongs at peak IP3. So that's just something that any customer can do. Let's say they go to a different voltage. Let's say they go to, we ran a 2105 last week at 2 volts. So that IP3 peaking is going to shift. So that's a new realm. It's a new voltage. It's far away from nominal. Run it at 2 volts. Sweep your current. Look where your peak IP3 occurs and put it there. So that's something any customer can do anytime they want. By sweeping V enable. Then the customer will say, okay, well, now that I find the right place to go and my V enable's at some value other than what I'm going to use, how do I rescale the bias resistor? The rescaling the bias resistor, you can come to apps. I have a presentation that tells you exactly how to do it, but all it is Ohm's law. All it is putting a current meter in line with your V enable line, putting a 0 ohm resistor in there so that the V enable you apply is the same V enable at the pin. Measure the current. You have a pin condition, V enable pin and I enable pin, and based on that, you can map that to IDDQ and use Ohm's law to set your bias resistor anywhere you want. So it's not difficult. I think it is, in terms of having a formal statistical analysis, we don't, because we don't test for IP3 in production, or we don't run it over temperature. But if you look at 4002, which is, I don't think I'm exaggerating by saying it's gotten into over probably 1,000 radios, different designs, and IP3 is critical in many of them. So I think that the variation is tight enough where it hasn't caused us any problems, even in applications that demand consistent linearity, and we've been in quite a few of them. So that's a qualitative analysis. Temperature. I've run just about all the devices at some point over temperature. I do that. Just about all of them, especially during the development phase, to make sure that things don't go awry. We do have, going back to 5112. The 5112, you do get quite a bit of, and the 5115. We'll stick with 5112. You do get quite a bit of bias current variation over temperature. It gets quite high going cold, and it drops some going hot. It doesn't drop to the extent going hot where you surrender on IP3 with the 5112. And the increased cold is it's not going to cause you a problem because you're not going to have a thermal issue cold. And very few people really go to -40 anyway. So it's not a problem. Wouldn't be a problem anyway.
Any of you guys call me Francis, and I'll kill you.
We found practical in production tests to set a 2070, for example, which has a nominal of 65, and we allow a window of plus or minus 20%. It's worked out well. To summarize, it's a pretty simple process. The customer can do it whenever you're running at whatever voltage. You can sweep the V-enable line to optimize. That's just for a single stage PHEMT device. Single stage PHEMT device. You can sweep the bias current and find a bias point for optimal IP3. It's just something good to know. The two-stage devices get more complicated. HBT, our HBT devices that we would be optimizing IP3 on, generally speaking, are two-stage, aside from the 2373 and the 2374, and I'd have to do more experimentation on those to see if it's simply IP3 just increases with bias until you hit a point where you have thermal issues. That could be the case, but I'll have to look at that. With the two-stage devices, you've got both of them contributing to your gain expansion overdrive, and that's a function of bias point. And you set that bias current so that you get flat gain over drive, which optimizes IP3. So it's a different type. You have something different driving your IP3. You've got the gain behavior, the two stages that govern your IP3 with our devices. If we do a single stage HBT like the 5710 that I haven't looked at a lot yet, it could just be more current, better IP3, which was what it used to be with the old HBT process we worked with a long time ago. More current, higher IP3.
Thank you so much for watching. If you'd like more information, please email us at sales@guerrilla-rf.com. And don't forget to subscribe to our channel for more content from Guerrilla RF.